Thank you for the kind introduction, Dr. Lau. Yes, I would like to tell you something about calibration of measurement devices and data evaluation, but especially calibration of measurement devices, because the calibration of a measurement device or of measurement devices is necessary if you would like to measure something. And if you would like to measure something, you has to know at first a little bit about the importance in the history of metrology, measurement and instrumentation. That I will short a little bit. Then the next step we will not do, that is only one slide. But the third point is very important, the measurement system as an information system. A measurement system is an information system because the task for the measurement system is it to deliver the information how heavy is something in compared to a standard. You have a standard, 1 kilogram, and the task for the measurement system is how many times so heavy is that as a standard. If you say you would like to measure 5 kilo, you put it on the balance, the information what you get is this is 5 kilo, and that means 5 kilo is 5 times heavier as a standard which is located in Paris. That is the information. And all these devices have a static behavior and a dynamic behavior. The static behavior is how the connection between the output and the input side is. Show the device really 5 kilo when you put 5 kilo on the balance, or show the 6 kilo, then you know there is a mistake in, but it's a static behavior. And the dynamic behavior is how fast get you the value. When you put the 5 kilo on, how long does it need until you have a stable value on the output side? So, and then we have another kind of errors, so-called random errors. Random errors are errors where you know nothings. When you have random errors, you don't know how big they are, when they occur. The sign you don't know, is it plus or is it minus? And when you have random errors, you can only describe these random errors. I will show you roughly how to describe the random errors. But the next point are systematic errors, and systematic errors are errors where you know everything. You know how big they are, when they occur, and if you know about this, then you should correct this. When you you stay not on a balance, the balance should have a linear behavior. Y is mx plus n. This is the output side, that is the input side. When you put nothings on the balance, then is the m unimportant, it's 0. When y is not 0, you know that n is not 0, and you know that's a mistake. And this mistake you have to correct, that you correct this plus n by a correction function, a correction number, plus kn, which has to be minus n, that it is 0. Because when you go on a balance, you put 5 kilo on the balance, you expect 5 kilo on the output side. If you put 10 kilo on the balance, you expect 10 kilo. Therefore, the ideal function of every measurement system is y is x. This is every time the aim, and all about what we speak in the following in the lecture is how to get this function y is x about the whole system. This is the output side, this is the input side. When you have a thermometer, you put 20 centigrades in, you expect 20 centigrades on the output side. And that is the aim, that every device is working according to this function, but life is difficult. So most devices don't work according to this, and you have to correct this. The systematic errors you have to correct, and that is what we call calibration. And therefore, the next points, movement of a characteristic curve, correction of a characteristic curve, that is a calibration. Then we have the point separation of random and systematic errors, because, as I said, life is difficult. Mostly you have mixed both. The random errors and the systematic errors, you have mixed them. That means at first you have to separate them, then you can describe the random errors and to correct the systematic errors. So, and after this, we have an example for the correction of a characteristic curve. That means the calibration of a measurement device. I have an example, and we calculate this so that you see in the end how looks the software on the computer which calculate the right measurement results. Then some expressions, range and precision, that is important. PC, and then you get the numbers on a PC. Today, normally we convert in an electrical signal. In the past, was it partly also pneumatic, hydraulic, and so, but today we make it every time in an electrical signal, every time, because we have the computers and all the electronics, and that is very easy to use for the processing later. Therefore, that is today not anymore a question. We convert in an electrical signal. So, when you have to convert it in an electrical signal, you have maybe in the beginning, let me say 20 centigrades. You have a sensor, any kind of sensor, and I say the measurement range is 0 to 100 centigrades. That's the range. The measurement value, the measurement sensor delivers 3 microvolt to 83 microvolt. 3 microvolt is 0, 83 is 100. So we can do nothing with this. That means we should amplify it. We should amplify it. We have an amplification here. These two resistors fix the amplification, and we can also fix the 0 point. Many amplifiers have it separate. You can here fix the 0 point, so that you say, I would like to have the 3 microvolt on the output side on 0 volt. And the 38, let me say, on 5 volt. That means Y is mx plus n. N has to set 3 microvolt to 0, and M, the amplification, have you to set that 83 microvolt leads to 5 volt. So now you can use an ADC, analog digital converter. Analog digital means you have an analog signal from the input side and a digital signal on the output side. If you have here, for example, a 12-bit ADC, 12-bit, from where to where is the 12-bit running? 0 to what? What are 12-bit? Difficult? 2 powered by 12 is 4096. Yeah? But this is a number what the PC get. Only this. That means when you have the temperature here, the PC get numbers between 0 and 4096. When you have completely different it here, if you have a pressure sensor, he gets the same. If you have here a balance, you put 5 kilo on, convert it in an electrical signal, you have the electronic, you get the same. So that means the computer need and program and a software how to calculate from this single value the true input value. The 100 or what 80 centigrades or 50 centigrades or what else, what you have here. That has to be calculated by the computer from this output value. And that is what I would like to explain you, how that works. When we look here, we have the electronic. You have to make the signal reconversion. That means on the output side, you have here to display 20 centigrades when you put in 20 centigrades. You have the screen, a printer, a display, or what else, or you can also have a loudspeaker or what else, but that is the output side. But important is what you put in, 20 centigrades, for example, 20 centigrades should be 20 centigrades here, or from the information technology, we know where you have a source, you have also a drain, and the drain is the Y. Here's the human, the waste basket, or what else. But for us, important are these three points. The signal conversion to an electrical signal, the processing, the analog digital converting, then the PC, the reconversion of the signal to calculate the true value, the X value, and to display the true value. This is for us important. So I jump a little bit. Yes. Therefore, at this point, you can say, this is an error, because this is not your final result. That is not the Y. That is not the Y which is equal X. You have, for example, here, let me say 82 centigrades, and this lead may be, I don't know, 3681. That means this value should lead to this value computed by the PC. That is important. Now have we a second point, or let me explain it from the error. You can say that the error is Y minus X. That is the error. Also the direction is important. The output minus the input. E means the measuring error, Y means the measured value, the output value, and X means the true value of the measure, the input value. The direction is also important. When you control, for example, then you have to know the sign. If you measure 20 centigrades, but the true value is 21, you know you measure -1 centigrades. When you would like to control the room, is a sign very important, because -1 centigrade means you have to correct this with +1 centigrade. When you control and you have the wrong sign, the controller would heated up the room instead of he is cooling the room. That means he's running in the end of the range, and you can do nothing. A wrong sign means every time that the controller is running in the end of the range to the upper or to the lower side. Therefore, the sign is very important. So here you see a systematic of measuring errors. You have here the measuring errors, you have the random errors, and you have systematic errors. Random errors are errors where you don't know when they occur, you don't know the sign, you don't know the amplitude, mostly all three things you don't know. But when you don't know, it's automatically a random error. And the random error would lead, you have, for example, 82 centigrades here. And you measure, and you have here 3,681. The next time you measure, you have 3,683. And you measure again, and you have 3,679. That means you have a slight scattering here. It's not exactly the same number. And that is a random error, because you have here a stable temperature. But you cannot correct this error, because you don't know in which time have you which value. You don't know it. These values are random errors, and we will see these errors we cannot correct, we cannot calibrate. We can only describe them in the end statistically with the statistics, but we cannot correct them. We can try to avoid them, to make them smaller, to shield the electronic, for example, that we have no influences here from outside, which can be the source for these random errors. But we cannot completely avoid them. It's then a question how big they are, but completely to avoid is a random error or not. That are random errors. But now, on the other side, we have the systematic errors. Here we have the systematic errors. And the systematic errors is the difference between this value and the true value. And you see, when we put this value in the output, you would say 3,681, that's not 82, not 82 centigrades. That means we have to correct this value to the 82 centigrades. And so, I would like to explain at first the description of the random errors. In the next step, I would explain you how to correct the systematic errors. Then in the next step, we mix both systematic and random errors. That's life, so is life. In the end, you have all mixed. We will separate systematic and random errors. In the next step, then, we correct the systematic errors, and in the next step we describe the random errors on a concrete example. And then have you everything what you can do with a measurement device in the frame of calibration. So that you know a little bit the next step, the next steps. At first, I speak about the random errors. When you have scattering errors, when you have scattering errors, what can you do? Mostly, random errors are running according to the normal distribution. Not all, we have also other distributions, but the most are running according to the normal distribution. And when you have a measurement row, let me say so, this is one, you measure and you have scattering values. And you have another one, and much less scattering. Which one is better? This one, of course. Now is the question, what have you done? Why have you found that this is better? That's true, of course, but what have you done? What have you compared? What you have compared is this. The differences to this is much smaller. This can be the mean, for example. This can be the mean. This is also the mean. Let me say mean 1, mean 2. But when you calculate the differences, the mean over the differences, you get this mean. And when you calculate the differences here, the mean over the differences, you get this mean. That means the differences over the mean, the mean over the differences is not a sign for quality. But what can I do? I can do following. I can take the absolute value and say, when I calculate from the absolute values, so that we have no minus values, when we calculate the mean over the distances, then have we here a bigger value as here. And that's a sign for the quality. You have here smaller values, smaller differences. Well, let me make it here. So what said we? We calculate the differences mean minus y of the single value. So that's this differences. And now we would like to calculate the mean over the differences, but because we have plus minus, we could come on the same mean. I have told you we can take the absolute values. Mathematically, the absolute values is difficult, but what we can do is we power by 2. We power by 2, then have we only positive values, calculate the mean, but we have to take the root in the end. When we calculate the mean, we have to add all those values from 1 to n, so much values as we have, and we have to divide by the number, but the number minus 1. Why is the number minus 1? Why not the number of measurements? Because with the first measurement value, you know nothings about the scattering. Absolutely nothings. The first information about scattering you get with the second value, because the second value is the first comparison to the first value. And therefore, you have to divide not by the measurement values, you have to divide by the comparison values to the first value. And that is every time n minus 1. Of course, when you have 999, for example, and you divide by 999 or by 10,000, that makes nearly no difference. But when you have small numbers, then it is important. So, and what we have here, that is already that what we call in the mathematics as the variance. And the variance is a quality parameter for a measurement function. When the variance is bigger, then is the quality worst. When the variance is smaller, is the quality much more better. The problem is only the variance, the unit of the variance is the powered by 2 unit of the measurement value. When you measure 5 kilo, y is 5 kilo, y, the mean for y, then you would not like to say the quality plus minus is 5, not 5, but let me say 0.2 would a little bit much. Oh, sorry, that is a German comma, 0.2. That I explain it later. In Germany, the comma and the dot is changed. Yeah, therefore, you must pay attention. When I use the comma, I mean the dot, and that is important. Also in the pictures, I have not changed it any time. But when you have 5 kilo plus minus 0.2, and that is a variance, then have you here kilogram powered by 2, and that makes no sense. And therefore, in measurement and instrumentation, we take the root. We take every time the root. That means the standard deviation is the root of all this n minus 1. N from 1 to y minus, incorrect, powered by 2. And when you look, this is already the standard deviation. This is the standard deviation, so as we know it, as the standard deviation. You have it here, the standard deviation. Oop. You have it here, and you see that's exactly the same formula with n minus 1. An additional explanation to n minus 1. Let me make an example. Yeah?
Standard deviation and root mean square error is more or less the same?
Excuse me?
Root mean square error. Root mean square error.
The root mean square error?
RMS.
Yes, that is exactly this. Yes, yes. But that is the normal standard deviation on the standard deviation of a normal distribution. Yeah? So, let me make an example. I have told you when you have 10,000 values, it makes nearly no difference. If you divide by 10,000 or by 999, it's nearly the same. But if you have very less numbers, very less measurement values, then it makes a very big difference. For example, you have 3 measurement values, 3 following numbers, 3, 4, 5, or 14, 15, 16. 3 following numbers. And we would like to calculate the mean and the standard deviation. At first, only by thinking, what is the mean? It's clear, that's the mean. It's in the middle, of course. This is the difference to the lower value. The difference is 1. This is the difference to the bigger value. The difference is 1. That is the difference. When you power the difference by 2, is it 1? When you calculate the mean over the 2 differences, it's 1. That means when you take the root, the root from 1 is also 1. So we are in the end of the formula. That means the standard deviation has to be 1.0, exactly 1.0. You have to divide by 2, not by 3, because you have to divide to the comparings to this value. And then you get exactly 1.0. If you divide by 3, you get something 1.7 and a little bit. And it's not true. With this small trick, you can also check your computer or your pocket calculator that you have the right standard deviation. Because this is the standard deviation of the sample. And that is what we use in particle measurements. The last lecture was about particle measurement. that is what we use in measurement and instrumentation, because we can every time only measure a limited number of measurements, never infinite. There exists also a formula where the mathematicians divide by n. That is then written as Sn. What we need is n minus 1. That is what we need. This is only for the mathematicians, because this is under the condition that the n is going to infinite. But that can we not do in practical measurement. In practical measurement, we have a limited number. It can be high, of course, but never infinite. So therefore, you can check with these 3 numbers, your pocket calculator. When you get exactly 1.0, then it's the right formula what you have. So, yeah, that is what I have now already explained. You see the better and the more worst measurement row. Another point is the mean. The mean is one of the most important parameter for scattering measurement values. When you have scattering measurement values, the mean and the standard deviation, that are 2 very important parameters. But the mean is also depending from, let me clean it here. The mean is also depending from the number of measurements, the precision of the mean. When you have a measurement row, that's the measurement row, you have again this scattering measurement values, and you calculate the running mean. That means you take the first and the second, calculate the mean. Then you take the third and calculate the mean. Then you take the next, the fourth, and calculate the mean. The fifth and calculate the mean. Then you will see that the scattering of the mean will be smaller and smaller. It should be so difficult to sign. But it's clear, when you have 10,000 measurement values, for example here, then is the 10,001st makes not a big difference. And so the difference will be smaller and smaller and smaller. Theoretically, when you could measure an infinite number of measurements, then you would come to the so-called expected value of the mean. The expected value of the mean has no plus minus. That's a concrete number. The mean, when you cut your measurement row at 100 or 10,000 or 20,000 measurements, you have a delta of the mean That means a delta of the mean, and this delta of the mean is coming from the natural scattering. This delta we can calculate. This delta plus minus delta of the mean. This delta we can calculate, and we will see how we calculate this. This delta we can calculate, and that is important to know when you have a measurement row with, let me say, 100 measurements, and you would like to repeat it. Let me say the Japanese have done an experiment, and I would like to check this. Is it right what they have done? And I do everything exactly so as they have done it, and I take also exactly 100 measurements. Then the Japanese can get this value and I can get this value. And then is the question, is this the same? Is this the same measurement? And we can say if both are inside of this delta, then it is the same. When I measure this one, then is it completely different? That's a different system, or I have the measurement conditions was different or something. But that is not to explain by the natural scattering of the measurement row. And now is the question how to calculate this. What is going into this delta y mean? What is going into this delta? Of course, this delta must be bigger when you have, let me write it, when you have a bigger scattering. When the standard deviation is bigger, then is this delta bigger. When the standard deviation is very small, then is also this delta smaller. That means that has to run according to the standard deviation. Another point is important, how many measurements I have. When I stop here at a lower number, the delta must be bigger, as when I stop here, where I have more measurements, the delta is smaller. That means if you have more measurements, the delta will be smaller, and therefore you have to divide by the root of n. The root, because that is a mathematical law of big numbers, that everything what is according to the, or going to the, yeah, to the, to high numbers, then have you following not to the numbers, you have to following to the root of the numbers. That's a mathematical basic law. So that would be okay so, but we have one problem. The standard deviation, we have also the calculation of the mean in. You see here the standard deviation. There is also a calculation of the mean in. That means when you have a low number of measurements, the standard deviation has also a plus minus. And that is an additional uncertainty what we have. And the mathematicians have found that this additional uncertainty is going until or according to the student distribution. The student distribution is a t distribution. It's t distribution or student distribution. And this t distribution, we have a t factor, and we have to multiply with a t factor from the student distribution. And when I show you, as you see here, what I have explained for the estimated value, the expected value of the mean, the same have you for the standard deviation. That is an estimation for the true standard deviation, but you have to measure infinite number of measurements, therefore you can never measure this, you can only make an estimation. So, and Yeah, have I cut this? Sorry. No, here I have it. You have here the formula. The t factor from the student distribution that have the mathematicians calculated, we can take it from tables. That is a huge calculation, but we must not calculate it. And you see here how to use it. You have here the measurements, 5, 10, 20, and so on. And, oh, I have forgotten to translate it. More than 200 means that. That is a rest of German. More than 200. And you see, the single standard deviation means in this range are 68.3% of the measurement values. And when you have more than 200 measurement values, is a t factor 1. That means he has no influence. When we have the double standard deviation, 95.5%, more than 200 values, then is the t factor 2. That means 2s. That means t is in this case 2. He has no influence. That means 2s. 3s, you see, t would be 1 or 3 when the factor is inside of t, but more than 200 is t. But when you have only 5 measurement values, then, and you would like to know for the security for 68.3%, the delta y, you have to multiply with 1.15. And this 1.5 is the add-on because you have only 5 measurement values. That is the uncertainty of the standard deviation. You must add a little bit. And when you make an absolutely worst case, you have only 5 measurement values, would like to calculate delta y with a security of 99.7% to be absolutely sure that you are in this range. Then have you to use for the t 6.62. Normally it would be 3. That means you get a huge range, but the security is high that it is there in with 99.7%. But then have you the huge range. And so you can calculate this delta y and can compare different measurement rows so that you can say, is it inside of this delta y? Then is it the same? That's to explain from the scattering of the measurement row. But if that is outside of this range, then is something different. Then are these 2 different measurement rows, different conditions, or something. So when we look for the standard deviation again, we have here the standard deviation, and I have, here is that, by the way, here is that written. Important remark regarding dot and comma. This is German, 68,3. In English is that 68.3. This is 11,000,2, and this is 11,000.2 English, yeah? That are the same. Especially in the drawings, I have not changed it. Therefore, you must pay attention. What is comma, what is dot, what is German, what is English, a little bit, yeah? You see here the standard deviation, the standard deviation, and you have a standard distribution, and you have here the y in the middle, the y, and you can say y minus 1s in this field, or between this and this point, you have 68 68.3% of the measurement values. That means when you calculate a measurement value and you have, let me say, you have measured 10 centimeter, and you have calculated the standard deviation. A standard deviation is, let me say, 0.5 centimeter. It's a terrible device with this error, but to explain it. That means between 9.5 centimeter and 10.5 centimeter. In this range, you have 68.3% of the measurement values. In this range are 68.3 of the measurement values. And the good thing is now, this is the standard deviation, and this is a single standard deviation. When you would like to use the double standard deviation, then you say 10 centimeter plus minus 1 centimeter, 2s, double standard deviation, means in the range between 9.0 until 11 centimeter, you have 95.5% of the measurement values. And the same can you do with 3s. Then have we 1.5 centimeter plus minus. Then you know there are 99.7% of the values in. And that is very easy to handle. That is very easy to handle, and therefore we calculate every time with a standard deviation, because you can double this, you can say so and so much values are in. What I have explained now was the view back. That means I have in the past measured. And only from that what I have measured in the past, I can calculate the standard deviation. But interesting is also, if you have a single value in the future, let me say you have your standard deviation, you have your mean, the standard deviation is here. You have the plus minus s. We know in the past, as we have measured in the past, we have had 68.3% of the measurement values in. But interesting is, when I measure in the future one time, maybe the point is here, then we can ask, in which range is the true value around the single measured value? That is a view in the future. And I write around the single value again the standard deviation. I write the standard deviation and say the true value, which is with the highest possibility the mean. The true value is in this range, also with 68% of the probability. Have you questions?
For the future, when
Yeah.
we have range actually is a little bit off from the previous method.
No. That is only, you measure one time. And that can be here, that can be here, that can be here. But you write around the single value the standard deviation and say, in this range is the true value with the same probability with 68%. It can also be your measurement value is here, outside of the, you write the standard deviation and say the true value is with 68% of the probability in this range. But in this case, is it one of the 32%? Yeah, that is, in this case, is it a case where the 32% are valid, because that is outside. Yeah? Because you have every time only a probability, 68%. Or if you double this, of course, if you double this, then have you 95%. If you have 3 times this, then have you 99.7%, and you see here you are in, maybe, yeah? But then have you such a range. Further questions? Hopefully nobody is shocked. Okay, then then we have a look. Yes, from the past. Yes, that is every time the basic. Also, to data mine the standard deviation, you have to use the data from the past. That is every time the basics. But the single value, the security of the single value is important when you would like to control, for example. When you not know that the true value is in an acceptable range, you have a problem to control. And then possibly you have to take not one value, you have to build the mean from more values. That's
I think in control that's why we need to ensure that our system is stable. It's always go into that range. It will not go beyond that one.
Yeah, that is randomly. That is randomly. Where the single value is randomly. Only that you have in the past measured that, but also in the past you have measured values here and values here.
Oh, yeah.
And that is the same in the future.
Yes, because we just ignore that, right?
Yeah, yeah, that is the same in the future. Yeah?
So if you're saying that I have a thermocouple.
Excuse me?
A thermocouple.
Yes.
The sheet says plus minus 0.5.
Yeah.
And if I take the measurement and it falls within his parameters, which is plus minus 0.5, so which means my sensor is accurate to that
Yes.
degree. So is that what he meant by that falling in the future?
Yeah, when you measure with a thermocouple, you get the voltage. And the output signal of a thermocouple is a voltage. And that can scattering.
Yes.
So, for the determination of the standard deviation, you have to measure many times.
Oh, I see.
Then have you the standard deviation. But for example, if you would like to control in the future with a single value, you must, it must be clear that the true value is close to this single value. And then it is important to know how big is the range around a single value where the true value is in. Because otherwise you control, your controller make what you want.
The actual value that I wanted.
Yeah, yeah. Okay? Yeah, it's every time good when you ask, because it is every time easy to explain it directly in the frame of the content. So, some, yeah, let me say, especially some companies hated this scientific method to use with a probability and 68%, but that is a scientific method. the description of the random error with the standard deviation is the only one scientific method. And if you write a paper or a bachelor or master thesis or PhD or what else, you should use every time the standard deviation. But the companies like it not so. It's too difficult, too scientific. And therefore, when you read about the so-called accuracy class, that is an additional method used many, many times by the industry, but it's not a scientific method. It's not a, I will explain how it works. It is very easy, therefore the industry like it. The accuracy class is the maximum expecting error in percent of the measuring range. That means the companies say, never you will measure a bigger error. That is scientifically is it wrong, because the standard deviation is going from 0 to infinite. You can never say never. You can say 99.999%, but you can never say never. So, but the industry say never. What do? They say, I measure many, many times, look for the biggest error, the biggest single error. And then they say, I have an error, let me say, from the true value, the difference from the true value, 1.2%. So that I have measured already. And now, to be sure that the customer never measured a bigger error, they put a little bit on top. And that is not a scientific, not a scientific method. That is depending from what the company like, would they should be absolutely sure, or would they like, oh, a little bit advertising is also good. Then they make it, they reduce it a little bit. When you have, for example, measured an error from 1.5%, you have measured. One company say, I take the error class 1.5. We give a guarantee, 1.5%. Never you will measure a bigger error. Another company say, I'm not so really sure. For me, I can better sleep when I say 2.5 or 2. There is no rule, and therefore that is not a scientific method. But it is used very often in the industry. And you must look and pay attention. For example, if you buy a PT100, a thermometer, it's a resistance thermometer, PT100. It's a very often used thermometer in the industry. You can buy it, for example, with an error class. Error class is 1.5. That means 1.5% of the range is the guarantee that you never measure an error bigger than this. This has a price from, let me say, 80 euro. Expensive, very expensive. Euro, I cannot. 5. Yeah, 400 ringgit. Ringgit? Ringgit, yeah, ringgit. 400 ringgit. Very expensive. And then you buy another thermometer anywhere in a shop. There is written, let me say thermometer. There is written only for use in kitchen. Only for use in kitchen. And this thermometer has an error class from 0.5%. The error class is 0.5, and you pay, let me say, 20 ringgit. Very cheap, but it is much more better. You think so. But that is a risk. When you say, I have measured an error 1%, which exceeds this, then the company has to pay penalty. But they have written only for use in kitchen. What have they to do? They have to pay a sausage or a cheese or what else, what you have a problem. But this company use maybe this PT100 for the oil distillation to produce gas for cars. It's running around the clock. And when they say, I have measured 1.6%, then calculate they how many money have we lost from the gas production, which is running around the clock. That are millions of ringgits. And therefore, this company makes it better, a little bit bigger, the value. But that are all not scientific methods. Yeah, when I say put a little bit on top, that is not a scientific method. Yeah? But you must know what the error class is. The error class is very wide used in the industry, but in many cases is it good when you have only the error class. It is good to data mine the error again. It is very good to data mine the error again, and then you can see have the high need for security, or is it a company which likes the risk? That is another question. Yeah. So typical error classes I have written here: 0.2, 0.4. Electrical measurement and instrumentation is very often 1, 1.5. The higher that is more in the field of measurement of non-electrical quantities, but that are so typical classes. I have here an example. A voltage meter accuracy class is 1, range is 0 to 100 volt. That means 1%, the definition is in percent, that is important. Accuracy class 1 means 1%. That means 1% from 100. Here you have this 1 volt plus minus 100 volt plus minus 1 volt. But if you measure 10 volt, it is also 1 volt. That means the relatively error is much bigger. You have here 10 volt plus minus 1 volt that are 10% of the error. The relatively error is bigger. And from this comes the requirement to use the range so much as possible. To measure, we say in the practice, if possible, measure in the last third of the range. There is no calculation for the last third. That is only what is to use so much as possible. And somebody said the last third, but there is no rule for the last third. But you should use the range so good as possible, not in the beginning, so that you use the range, so much as possible. Therefore, here I have written the accuracy class is a compromise of an exactly error analysis, that is the standard deviation, and an easy usability, easy usability for the industry. Yeah, but it's a compromise. If you make a scientific work, you should use the standard deviation and the probability for the scientific proposals. Questions?
So using the 1% range, you can use it, but then you have to repeat with the standard deviation in order to correctly calibrate your sensor. So you take, say, the 1% class and then run the standard deviation.
No, this is only 1% or 1.5, that's different. That is depending from the device. But the difference is that the company say you will never measure a bigger error. That is the difference. And the standard deviation say in this range are 68% of the measurement values, but 32% can also be outside. Yeah? Therefore, the probability or that is important. Yeah? You have every time the connection in the scientific expressions, you have every time the connection to the probability. You can only say with never, for example, a scientist would never say when a father say, I'm not the father of this kid, for example. Then they make a test. They would never say, you are the father with 100%. They say, you are the father with 99.9999999%. Then you know you are the father. Yeah? But that is the difference between the scientific method and industrial method. Further questions? I think, what's that? Yes, I think it's now time to make a short break. Yeah, it's a half time to make a short break, and because we have then also the systematic errors, we have finished now the random errors, and we start then with the systematic errors. That is then the calibration of the measurement device to calibrate the systematic errors. How long should we? Yeah? 15 months? 15 months. 15 minutes. 15 months. Sorry. 15 minutes. Okay. 15 months. Yeah. Oh yeah, that's good. Yeah, that's good. I don't know why, but you must say. So it's okay? Okay. So, ladies and gentlemen, we have now spoken about the random errors and how to describe them. One is a scientific method with the standard deviation and the probability, and the other is the, no, that's not. The other is the error class, what we use in the practice, but not for scientific purposes. And now I would like to speak about the second kind of errors, the systematic errors. And I draw you here this small picture. You see the temperature, that is the input value, but your end is a number what you give into the PC. And that is every time the same number. When you, not the same, but the same range of the numbers. When you have a pressure sensor, you have also, if you use a 12-bit ADC, you have also the range from 0 to 4096. And if you measure there the speed, you have the same. And if you measure there, the voltage, you have the same. But that means the computer has to get and software with which you calculate from these values the true value, what was the input value. And for this I have here a very important picture. You have here the input value x. The input value x is the true value, what you put in your measurement device. Then you have a transfer function. A transfer function, I have here written a linear function at first. We will later also look for a nonlinear function, but the easier case is a linear transfer function. Then you get a value, I have called it y uncorrected. The uncorrected value. And the uncorrected value is, for example, this ADC value. This ADC value from 0 to 4096. That means this is a measurement device and this is a computer. Mostly the computer is also part of the measurement device, but when you split the measurement device, the sensor and the analog electronics, the analog digital transformer, and here you have the ADC number, and now you have the computer. What want we? We want that this y is equal to this x. That is the aim. 5 kilo on the balance, 5 kilo to show. 20 centigrades in the thermometer, 20 centigrades to show. Now you have here the formula for y uncorrected. Y uncorrected, you see here, you have here y is mx plus n, and this y is on the output side, this y uncorrected. This means here you can also write mx plus n. That can you write here. The question is, what should be n in the ideal form? When you have y is x, the n is 0. That means this n, what is included in y uncorrected, to this n you add a constant of kn, calibration constant. It is written with k because in German the calibration is written with k, not with c. Yeah, but that means calibration constant. The calibration constant for n, what has it to be? How do you calculate the calibration constant to n? When n plus kn has to be 0, then has to be kn minus n. So, and now we have the m in. You see, this is here placed, or you can see it also here. This is mx plus n, n plus kn is 0, and now the calibration constant for m multiplied with m has to be 1. M multiplied with m has to be 1. That means km is 1 divided by m. It's very easy. So that these are the calibration constants for the 0 point and for the amplification. And when you calculate this, then is it very easy to calculate, but you must know what you do. That is important. You must know what you do. Very important is to understand this picture, that you have here the transfer function, y is mx plus n. Here is the ADC number that is going into the computer. The computer has this formula to calculate y from this ADC number. This is a very important point. So, and that is the whole mathematics what we need. And you see that is nearly nothing. That is absolutely easy. You can calculate the m. Delta y divided by delta x is m. The km is 1 divided by m, because Km multiplied with m has to be 1. Then you can form in another way this formula. N is by uncorrected minus mx, so that you can say, you can calculate n, and because you say n plus kn has to be 0, kn is minus n, and you have here your correction function. That is a calibration function. You have here the ADC number plus kn multiplied with km, and then should this y equal to this x was what is contained in y uncorrected. That is the trick of the system. So let me show you some small examples, or one example, or one bigger example. When you have non-linearities, maybe this sensor is a non-linear sensor, also when the amplifier is a linear system and the ADC is a linear system, you get the non-linearity over the system until the ADC number. Then can you at first try that you use the whole range. Mostly we use this, that you bring the 0 point to cover and the biggest point, that this both points are in the range, so that you use completely the 0 to 5 volt. Other ADCs work from 0 to 10. Others work from -0 to +0, -5 to +5. That are the 4 typical ranges. Important is only that you use the whole range. If the amplifier, the analog digital converter use -5 to +5, then has -5 leads to 0, +5 leads to 4096. That you use the whole range, that you lose not resolution of the device. That is important. So with the amplifier, you take care that the lowest and the highest point is exactly on the voltage of the input range of the ADC. That is important. And then, if you have that, then can you look how to calculate from this value an value for the the output value from the measurement device. I have here an example. This is a length measurement, and you have 10 kilo ohm, 10 centimeters. That is a slider which is going from 0 to 10. And now we have had it in the past that this wire, from, let me clean it a little bit, that this wire from the sensor is in the air or anywhere. Here is the sensor. You have the plus 5 volt, for example. Normally you have here the wire. This is a slider which is going up and down, and you have here the output voltage without this resistance, only so. That is fantastic, because when you look here, you have the centimeter from 0 to 10 centimeter. This has 10 kilo ohm, this resistance. That means 1 kilo ohm per centimeter. Here you have the kilo ohm, the centimeter. Here you have the kilo ohm, and 1 centimeter is 1 kilo ohm. 2 centimeter is 2 kilo ohm, and because we have here the voltage, you can also write here the voltage, because the voltage is proportional to the resistance. That's a direct proportional, so that you have here, when you are at 10 centimeters, that is the highest point, 10 centimeter means you are at 5 volt. It's a completely linear system. Fantastic, we can use it. But if this wire is long, you have disturbances from outside. Somebody switch a light on and you have a flash, electrical field flash, for example. You have disturbances, and these disturbances are random errors. That means you have random errors in. To avoid this random errors, there is a little trick. You take here an additional resistor. This resistor has, I think, 5 kilo ohm, yes? 5 kilo ohm, and because this resistor takes a current over this system, you set it on a higher energy, and the disturbances from outside must be much more stronger to disturb this cable. Mostly is it so that this resistance will be placed directly on the output side, that you have it here, that the current from the 5 volt has to go over the whole cable, so that you have a stronger energy on the cable and less influence of these disturbances. But when we look now and calculate, we have a so-called charged voltage divider, and that is nonlinear, because you have here the slider that is linear, but you have every time exactly the same resistance as a load. And that means you get a picture. If you have the 10 centimeter here, the 5 volt here, it looks so. That is not so good normally as this, but these are systematic errors. These are systematic errors, and these errors can be correct. These random errors, what we have here, we cannot correct, because we don't know when they come, what the amplitude is. But the systematic errors can be correct. So we change, with this simple trick, we change that we avoid random errors, but we get systematic errors. But systematic errors are not the big problem. The random errors was a problem. Now we have a nonlinear function. I have explained that all with a linear function, but the difference is simple. You take some linear functions, some calibration points, and you make an approximation with linear functions step by step, so that you correct step by step, not over the whole function, you correct it step by step. And when we calculate the values, in Germany the students have to calculate that now, they have to calculate what is the voltage here, then get you these values, and you see here the nonlinearity. Yeah? 5 volt is here, 10 centimeter is here, but you see the nonlinearity. So, but the output voltage is the uncorrected value, because that is not the true value. When you have 1.35 volt, the computer should calculate 4 centimeter. And that can we do, and that is now a very important table. That can we do, that we calculate at first the linear function step by step. That means that is the point 0, 0. That is the x, the input value, y uncorrected, the uncorrected value. And you have seen 2 centimeter, we have 0.76 volt. When I switch back, 2 centimeter, you have 0.76 volt. 4 centimeter, 1.35 volt, and so on. You see this table here again. 6 centimeter, you have 2.03 volt. And now we make an approximation between these 2 points, between this point and this point. We take this linear function with this m and this n. How to calculate? I have shown you the formulas. The m is y uncorrected divided by delta uncorrected divided by delta x. Delta uncorrected means in this case 0.76 divided by delta x. Delta x is 2 in this case. So, and then we change the formula. N is y uncorrected minus m multiplied with x. And when you take this point and this m, it leads to 0. When you take this point and this m, it leads also to 0, because the line is going through both points. The line is the same through both points. So, and now we have to calculate the Km, the uncorrected the correction value. Km is 1 divided by m. Kn is minus n. Of course, this is 0, but you see here 0.17 minus 0.17, minus 0.01 plus 0.01, and so on. You see also, when you have 1, 2, 3, 4, 5, 6 points, when you have 6 points, you have 5 lines. Every time 1 line less than points, because the lines are between the points. So, and now, hopefully it will be clear now what we do. We take these parameters into a software. This is a software, I think everybody can read it. That is the so-called Turbo Basic. It's a very, very simple software. You can read it like a book. That's only a line number, but why uncorrected? You read into your computer the uncorrected value. Then you ask if this uncorrected value is less than 0.76. I switch back. This uncorrected value less than 0.76. If yes, the computer knows you are in this line, and you have to use this correction function. And no. So that means less than 0.76, use the first correction function, and this is only go to the end, print the result. But if no, if the value is not less than 0.76, then he asks less than 1.35, the next value. If yes, takes the next correction function. When we look here, that is the next point, less than 1.35. Yes, take this. If no, ask less than 2.05, take this correction function. If no, then go to this correction. So the next point and this correction function. So that you ask in which interval you are, and then can you calculate it. We can make an example. Let me say, the slider from the sensor is on, let me say, 5 centimeter. 5 centimeter. in the middle between 4 and 6. What is the value, the uncorrected value, what the computer get? Can you calculate this? What is the value that is the mean between these two? Yeah? At 4 centimeter you have 1.35, and 6 centimeter you have 2.03. And if the slider is on 5 centimeter, you have the middle between this both. Can somebody calculate it? I have not calculated this. The middle between 1.35 and 2.03. Every mobile phone has a computer, pocket calculator in today. And same is,
1.69.
excuse me?
1.69.
1.69, yes? So, the others too? So, now the computer would get 1.69. The computer don't know that this is 5 centimeter, but he should calculate with this 1.69 the 5 centimeter. Now read in why uncorrected is 1.69, and now look what is the computer doing. He asks if y uncorrected is less than 0.76. No. If y uncorrected is less than 1.35, then do this, but it isn't. The next, if y uncorrected is less than 2.03, yes. Then take this correction function and now calculate y as 2.94 multiplied with 1.69, this was the uncorrected value, plus 0.01. That should you calculate. You can say 1.69 plus 0.01 multiplied with this. What is the result? 4.999 and so on, 5. Yeah? And that's the aim. That's the aim, because the computer don't know that that was 5 what he get. The computer get only a voltage. But this is a rule to calculate from the voltage the true value. Because the 5 is now the y, but the y is equal to the x. And that is what we call calibration. These are the calibration constants for the m and for the n. But you have to ask the interval, because in this case we have a non-linear function. When the interval is too big, for example, if you have a point here, a calibration point, and another point here, and that is too wide, of course you get an error here. But then you have to put additional points in, so that you can calculate it step by step. Such a function, have you today in every washing machine or coffee cooker or what else. When you display a temperature, then have you exactly this kind of calibration behind this. Because the thermocouple or the PT100 also delivers only a resistance or a thermocouple a voltage or anything. But in the end, after the ADC, the computer get a number. In this case, I said the number is already a voltage, but the computer get only a number. And this number is not the measurement value, but it is connected systematically to the measurement value. And so you can calculate this. Have you questions?
So would it be wise to have a higher resolution? I mean, like to get it more accurate, you add more points of references. So, or is it just generally to divide them equally?
Yes, that's absolutely true. I have, for example, I said here we have used a 12-bit ADC. When you use a 16-bit ADC, you have, I don't know exactly, 65,000 points, so is this range, much more, yeah, a much more higher resolution. Then, is it so you can measure also with a higher precision because you have a much more higher resolution, and when you have then here a point and here a point, but the resolution of the ADC is so high that you see here the difference is as a mistake, as an error, then can you set a point between this. Then have you to use more calibration points. Yeah? Was that the question? Other questions? No more questions? Yeah, yeah. That's absolutely good.
Say that you have a lower resolution sensor. I say plus 1 degree Celsius for every change.
Yeah.
But you have, let's say, a more higher bit resolution EDC.
Yeah.
Would it actually affect errors in your results?
The device with the lowest resolution determines the final resolution. If your sensor has a lower resolution, it makes no sense if you have a sensor with a low resolution and then you put a very high resolution behind, because the resolution is the number of steps from the lowest to the highest value, 4096 in this case. But when your sensor delivers this, and you have then an ADC, and he makes a lot of resolution between this, it's not useful because the sensor say so or so, and you jump from the ADC a couple of numbers higher. That makes no sense.
So it's best to match both the sensor
Yes,
and your ADC.
yes, yes. The best would be if that's roughly in the same range. Yeah, very interesting question. That's very good. No questions anymore?
So like for the analog sensor, for example, analog sensor, do we have resolutions for analog sensor?
No, not resolutions, but for the analog sensor, of course you have an analog signal, but when you have an analog sensor that can linear or not linear, that makes no difference, you have every time small disturbances on. And the question is, how big are these disturbances? It makes no sense to use an ADC with 16-bit, where 1 bit is, I have not calculated it now, but maybe 1 bit is 1 nanovolt. And the noise from your sensor is a microvolt. Then you jump in your resolution of the 65,000 steps. Then makes it not a sense. That is also every time the problem. I have explained it with the 12-bit, but when you use an ADC with a higher resolution, for example 16-bit, that is not only that you replace the ADC, also the disturbances from the sensor must be low. The noise from the amplifier must be so low that you can use this 16-bit. And if you have a sensor, an analog sensor, which produces spikes or has an influence from outside, then makes it not a sense to use an ADC with a high resolution. You jump the, it can be that you use only 14 bits because the last 2 bits are noise. That's completely noise. And that can you not use. Noise is a random, is a completely random error. That is important to know. Noise, you cannot say when you have a peak and what's the amplitude, and that's a random error.
So in that case, you need to filter first the noise before.
Yes, of course. To avoid random errors is a wide, wide field. There can you do many, but for random errors you can only do it before.
Yeah, but for filter, so we cannot completely remove the
Yes,
noise, right?
of course.
Reduce it.
Of course, especially when you have a measurement signal where you know it's very slow. For example, temperature. A temperature will never change in the range of 100 hertz. Never. You can be happy when it changes in 1 or 2 seconds. That's very fast for temperature measurement. So that means all above 1 hertz you can filter. But difficult is when you have fast measurements. Pressure measurement, for example. If you have in pressure pressure frequencies from a kilohertz, that's possible. Then can you not filter disturbances in this range? Because that is also your used signal. And then it is difficult. Yeah? Okay, then we have a look for the. So, now the next point. We have now corrected the systematic errors, but in practice you have normally mixed both. You have mixed systematic errors and you have mixed random errors, both together. For example, I have here the example of 10 centimeter, let me say 10 centimeter, we have measured and we have measured different voltages. You see here that is the mean, the y uncorrected is the mean, and you have the scattering around this mean. And therefore, the mean is this part of the error what has a systematic character. The mean represents the systematic part of the error. That means when you calculate the mean, that are the single measurement values. This is the mean. That is the systematic error. The difference between the mean and the true value is a systematic error. You can correct this systematic part. And when a single value is directly on the mean, is equal to the mean, of course, you use this function and you get exactly as y the true value. But when a single value is bigger as the mean and you correct with the same function, then have you a value in the end which is bigger as the true value. That means the random error you cannot correct. You can correct the systematic part, but the single values, when a single value is smaller as a mean, you get also a smaller result. That means the separation of random and systematic error. The keyword is calculate the mean. Correct the mean to the true value, but when I would calculate here the single corrected values it would be a scattering around 10 centimeter. The mean would be again 10 centimeter because you have corrected the mean of the uncorrected values to the 10 centimeter. Is that to understand? That is an important point, to split the errors into the random and systematic errors. So then I will explain an equipment what we have. An equipment that's we have it in our lab as a demonstration model. Last year we have had a little bit more time for the lecture. We have done the experiment also, but this time we have also another lecture, particle measurement, and, and therefore we have cut this a little bit. But this is an experiment and we can calculate this. That should be a sensor. You have here a light source. You have a reflector. That can be a mirror or something. You have a sensor that is a photoresistive sensor. That means when the light comes back to the sensor, you can measure the resistance of the sensor and can read in the resistance into the PC. And now is the question, how is it looking? When you have this equipment and you have a reflector, let me say here is a reflector, that should be a reflector. You have your sensor with a light bulb and let me say a little bit longer maybe, and you irradiate the light to the reflector. That is a reflector. And you look with your sensor to the brightness of a point. When you have now the distance between here and here, that should be the distance. What have I used? I have used the S. I think it's better the S we have used for the standard deviation. You can say the length, for example. The distance between my sensor and the reflector. What do you think when I have here the light intensity? The light intensity in candela is now the unit. That means the light intensity. What do you think? What is a curve? Linear, non-linear? If you move it far from the mirror, will it be brighter or darker? Darker, of course. That means it starts at a point and will be darker, of course. How will it be darker? Linear, it's not so good. Linear would mean you cross the x-axis. What is under the x-axis? Minus light that don't exist. It can only be dark. That means it cannot be linear. It cannot be linear. It must go in the infinite against zero. So, but how non-linear? So or so? No, the chance was 50-50. No, you see, when I look to this, you see here's a light. When you move it back, the light will be bigger. That means it's powered by 2, or the root function. Because you have the same amount of light on a bigger area. On a bigger area, the same amount of light on a bigger area means it must go down in this way, powered by 2 function. But two things. When you go far away, anywhere you are here, there is light which is going into the nirvana. It's lost completely. That means anywhere here, maybe you have an additional nonlinearity, additional to the theory, because you are out of the mirror. But also this is a systematic error. And also this can be corrected, because it is every time exactly on the same place come you over your mirror. It's exactly the same place. Therefore, is that also a systematic error? Another point, when you come closer and closer, it will be brighter and brighter. But anyway, you are on the wall, it's dark again. That means exactly what you say, it means it goes down. It's again dark. That means we cannot measure here, because this point would be the same brightness as this point. That's the same brightness, we cannot measure. We have to make a limitation for our measurement range, that we say we can start at least at, in this case we have 50 centimeter, we can start at 10 centimeter before it's going down. When you come a little over this, then works it. But when you see 9.9 or 9.8, you know you are out of the range. And no error is valid, no standard deviation is valid, nothing. You are out of the range. And so, in the end, of course, you have also a limitation, for example, by 50 or so. It's then depending how far can you register the light. Anyway, you have so much influences from outside, from other light sources, that you cannot measure anymore. So that you have to give also a limitation from the upper range, the upper number of the range. So, and so that is the equipment. And now that is a task I calculated for you, but normally the students in Germany have to do that now. Then have their half hour or a quarter hour time, and then we check it. That is now everything in what we have learned about systematic errors and random errors. At first, you have to calculate the uncorrected transfer function. Important is that you have in your mind this picture. X is going into the device, that is a transfer function. X is going in, Y uncorrected is going out, Y uncorrected is going into the PC. You have here the correction function. Y is going out under the condition that X and Y has to be equal. That is a condition. So, when you now look, I have here the table, or I have told you that calculate the uncorrected transfer function, that is this one. Calculate the correction function according to the linear approximation. Linear approximation is that what we have done with lines. That is a linear approximation. This is this one. Calculated the corrected transfer function, that would be completely over the whole system. If that is everything right, it is Y is X. That's overall. So then you should draw the three functions. Then you should write the correction software. That's every time important, because that is the software what you have in every device. In your washing machine, where you display a temperature, is exactly the software behind. The software can be written in every language, of course, but the content has to be the same. Then you should test the software, what we have done with the other task also, between the points, because the sensor can be on any place, also between the calibration points. And then you have to calculate the empirical standard deviation from the system as a scientific method to display the random error. And you have to calculate the error class of the measurement system so that the industry is happy that they have also an error. So that is a whole task, and you see we have measured 10 centimeter, we have measured many times, 10 times I think, yeah, 10 times. And you see you have a scattering values. 20 centimeter, you have scattering values, and so on. But it's a scattering around a mean. And the mean represents the systematic error. So that we can set up, that is a mathematics, but I show you that later again, that you can set up this table. Exactly the same as we have had it in the first example. It's exactly the same principle. You have 10 centimeter, and that is a mean from all measurement values at 10 centimeters. This is a mean of all measurement values at 20 centimeter. You have to calculate the m, you have to calculate the n, you have to calculate the km. Km is 1 divided by m, and kn is minus n. You see here the correction function, the calibration function, and here you see the transfer function. You see also the constants have all units, and if you calculate with the units, you should also get the unit in the end. So the mathematic, you see, it's absolutely simple. Absolutely. That is primary school, I think so. In the end of the primary school, you should know that. But, and that is also that what I say every time to German students, but you must know what you do with these formulas. The formulas are easy, but you must know what you do with the formulas. M is delta y uncorrected divided by delta x. N is y uncorrected minus mx. And that is then between the corresponding calibration points. And then Km is 1 divided by m, Kn is minus n. And you see you have one line less than calibration points. So we can write the software. It's the same principle. We write the software. You say y uncorrected less than 0.74, then use this line. When we look into the table, you see I ask for this, less 1.74, use this. 10 centimeter would be here. I ask not less than 1.4 because 1.4 would be here. That's the first point at 10 centimeter. Less than would you be here, but that makes no sense. There fails the system. Therefore, I ask for the second point. I ask for the second point. If I less than this point, use this line to correct. The next point, I ask less than this point, use this, and so on. If you have you have maybe here some more in, If necessary, you have to set some points if that is a strong nonlinearity in a short way. But important is the last point. I ask, for example, here, less than this point, calibrate with this. And this is, let me say, 50 centimeter. Here I ask not less than this point. Here I ask less than this point, bigger than this point, take this one. Why do I that? Why do I that? You see, here I would ask less than this point, use this. But now I ask not less than this point, use this, because that are measurement values, and a value can also a little bit bigger or smaller. What do the computer when he get a bigger value? He don't know what he should do. He would run through the program, but he don't know what he should do. And therefore, for the last point, I ask bigger than this point. You ask at first less than this point, use this. Bigger than this point, use the last line. That means when you have a value which is bigger than the last point at 50 here. The last point. For example, you have a voltage 2.3 volt. It's a random error on. Then the computer would say it's also bigger than this point, and you can calculate a value. And when you have a value here, he would use the same line. But if you are far away, the error will be bigger and bigger because you are out of the range. With 2.16, you calculate 50 centimeter. If you are at 2.2, you calculate more than 50 centimeter. You know then you are out of the range. You stay in the last line and change not the line, also if you are anywhere. Therefore, the last point is then the question bigger than. Here we have it, and we can do the same game again. Let me say your sensor is on 35 centimeter. You should calculate 35 centimeter in the middle of this. Can you calculate this again? We try it again, and then we go into the software and look. Get he 35 centimeter or not? The mean between 1.9 and 2.0, 1.95 or so. What is the value? $1.9651. Yeah? 5.5. Yeah, but it is 3 behind the comma is fine. So, and now go in this software. He asks less than 1.7, no. Less than 1.9, no. Less than 2.0, yes. That means you take here 1.965 minus this multiplied with this. Sorry? 34.9. Yeah, 35, roughly 35. Yeah, so that you calculate the y, then the y here, then as 35 centimeter. And if you are anywhere between these values, you get a voltage. And if you put the voltage in your software, you get the centimeter as the right value, the corrected value. That is what we call calibration. Have few questions? Okay. So these are the lines, the uncorrected function. You see here a little bit also when I draw it in one picture, you see a little bit how it works. Let me say you have here the input value x, and this is y uncorrected. Y uncorrected, that is a transfer function. Let me say it looks so. Now you have to calculate the correction function. Y uncorrected is going in, y uncorrected is going in, and y is going out. Y is going out. But this y is equal to x. That means you change the axis. That means if that is a transfer function, then is this the correction function that is a mirror on this line, and this line is y is x. It's exactly the mirror function. That is what we do. And if you switch the correction function and the transfer function and the own mirror function behind each other, you get y is x. The linear function y is x. And that is, every time that's what we want. 5 kilo on the balance, 5 kilo on the balance, 5 kilo out. Every time that's what we want. Oh, my computer makes, I have not used the, but we are ready also now. I have not used the power supply. So, I would like to explain shortly the rest. This is the table what we have in the beginning, but now I have corrected all the single values. All the singles value I give over the software. And you see you have the single values scattering around 10 centimeter, scattering around 20 centimeter. The systematic part is corrected, but the random part is still there. The mean over this should be 20, the mean of this should be 10, and so on, because we have corrected the mean to the true value. But the random error is still in. And so we can calculate the standard deviation over each line. And normally the standard deviation you will find in the last line, because the standard deviation is an absolute value. You see here, in this case, plus minus 4.84 centimeter. That is an absolute value, and the absolute value is there the biggest, where you have the biggest numbers. That's the case. Normally you find it in the last line. For the error class, you look where have you the biggest deviation from a single value to the true value. The biggest deviation. That can also be in a lower class. In this case, is it not in a lower class? We have measured here 58.65 centimeter. That is the biggest what we have in this table. The biggest is 17.3%. That's a terrible measurement device. of course. If you have such a measurement device, you can put it in the rubbish. But it is to demonstrate the random systematic error, therefore we won't have a random error. But you have already measured 17.3%. That means the manufacturer say the customer should never measure a bigger value, and so he put a little bit on top, 20%. You can also say 25%. There is no rule. Therefore, that's not a scientific method. But here you have now you have corrected the systematic part, you have determined the random part, you have described the random part with statistics, with standard deviation, as a scientific method, and with the error class as an industrial method. And you see here also that would you measure. And when you measure now again, the device should, when you are at 20 centimeters, the device should measure measurement values around 20 centimeters, also for the future, because it is calibrated now. Have you questions? No. Then I think I'm 5 minutes over. Tomorrow we cut it by 5 minutes. Thank you.